So, welcome back from the break. Couple quick announcements. Today is our office hours in D215. Tutorials start this week, so that'll be on tomorrow in FNH 30. Canvas Quiz 3 is going to be opening up this week, and again, due next week through that point. We're going to have a series of Canvas quizzes moving through to that point. Midterm, average was 71.8. You guys did very well. Congratulations. Round of applause for everybody. I'm still finishing the sort of midterm walkthrough, so this is a series of videos of how to do each one of the questions that we actually saw. Those will be posted later this week. Regrade requests. If you have a regrade request, please post it up using Gradescope. Now, quick note about regrades. The way regrades work is I have to regrade your whole paper. So you can do cite. If this is a problem you think has happened, you want me to look at one question, absolutely say this is the question I want you to look at, but I will have to go through your entire mark, which means if you have extra parts somewhere else, you may lose those. So this means your regrade, your mark can go either up or down. I'm just mentioning that part out because there have been cases where somehow magically you got 10 out of 10 when it should have been a 0, and then I catch it on the regrade, right? So this is a point to look through. Midterm 2 is going to be March 24th at 6 p.m. Final exam has now been announced. The final exam is going to be on the 15th of April. I don't think we have a room booking yet, but this should be put up. All right. One other thing, too. Coming up on Friday, March 6th, we've got our first Undergraduate Chemistry Society meet and greet. What this one is this is about if you'd like to meet with other chemistry faculty, this is a great way for you to meet potential research groups that you're looking into getting into. So at 3:30 to 5 p.m. is research group presentations. 5 to 8 p.m. is Wine and Cheese hosted by the UCS, the Undergraduate Chemistry Society in Chemistry. If you have any other questions, please do contact them, but interested if you guys are to come and join. So last class, we introduced you guys to conversions of acid chlorides and anhydrides into amides. And we also talked through how we did what we call the Schotten-Baumann reaction. This is the physical version of separation where we're using one of our equivalents of our amine as our kind of base. It's using to migrate a proton between an organic layer and an aqueous layer. And we're using something like sodium hydroxide, an inorganic base that would normally be stuck in the aqueous layer. It's using this physical miscibility way to sort of move things between two different phases. We also introduced you guys to anhydrides and mixed anhydrides and how those reactivities can be used. So, quick reminder. If you have these conditions, this is your molecule. What is your product? Okay, so let's work this out. When you're asked to work at a question like this, it's important to survey different pieces of it. Your eye has to move between a couple different parts. First, there's your starting material and your reaction conditions. And based on that coupling, you should identify a functional group of which your chemistry is going to happen at. Basically, you're trying to target and say, given these conditions and this molecule, what part do I need to pay attention to? So what does this kind of look like, or what functional group in my starting material should I be focusing on? The cyano or the nitrile. That right there is what we're going to put our chemistry in, partly because, remember, up until now, we don't have a lot of ways of manipulating this benzene, the aromatic group, so we're going to focus primarily on the nitrile. All right, what type of conditions are these? If you had to describe them, they are basic. Okay, they're basic. Aggressive, not aggressive. If you look at the conditions, what does this kind of look like? Are we pushing hard or not? Well, we've got heat. and we've got water. This sounds like something like we're using basic conditions, absolutely, and we're probably a little bit forcing, potentially. The other way I could make this more forcing is lots of time, right? If I said that I had to heat for an extended period of time, that's another thing that I'm telegraphing if I added that component. So like right now, you've got basic conditions, you got a nitrile. What do you think the product is? There should be kind of two things in your head of what this is most likely. Yeah. Amide is option one. So that would be hydrolysis using basic conditions of your nitrile, and it's going to stop here, right? If you keep going, this amide, remember we said that this is absolutely, that's under basic conditions, this is where it's going to pause, that's the intermediate that you're going to generate. If you keep going, more time, more heat, more base, what happens next? Yeah, eventually it will stop at the amide, but if you keep pushing long enough, you will get back over here. Right? So your two decisions of this one would be basic conditions are unique because the hydrolysis of your nitrile will pause, will move through this amide, the primary amide, but the primary amide has a possibility to move through your carboxylic acid. That's partly why we're going to talk about this today, because you can actually reformat your amide into the carboxylic acid. This just takes more, wait, let's do it right, more base and heat. Come on. You guys just were on break. This should be... Point is, you can actually get the second step to work. You're just going to have to push it harder. But it is a reaction that we can do. And what we're trying to telegraph with that statement, the amide is your stable stopping point. Using things like Le Chatelier, excess material, higher temperature, we can actually push it through to the carboxylic acid. So that's what we're going to talk about today, is conversions from amides. If we have an amide as our product, how do we complete this diagram of using the amide to reformat to other materials? Even though down at the bottom, this is our energetic sort of sink, we can actually do amide hydrolysis and amides to nitriles. This is another big jump off. We're going to talk very quickly about interconversions of all the entire space, because this is our final sort of conversation about carboxylic acids and nucleophilic acyl substitution, and then introduce our isocyanates and other organometallics. So as we discuss this out, amide hydrolysis just means taking your amide and breaking it back into your carboxylic acid. Now, if you remember on our energetic tier, this is actually walking uphill a little bit. We're going energetically. Amides were our most stable one, which means we're going to have to use things like large excesses of temperature, large excess of material, strong acid and strong base. It's possible, but this is sort of our sort of chemistry of last resort. So almost always, extended heating, we're using time and temperature is what's necessary to push these parts through. Just in general, acid is definitely easier than base. So under acidic conditions, remember this is our mechanism we've walked through before. Starting off with a molecule like this and talking about the acyl substitutions we discussed, what we're kind of doing here is I've got conditions where my nucleophile is going to be water, right? My electrophile is my amide. Neither of those two things are amazing in terms of overall reactivity. The amide's very stable, not very electrophilic. The nucleophile water is not that nucleophilic. It's not a negatively charged species. Under acidic conditions, though, what we're doing is we're using the acid to activate the carbonyl first. What we're doing is we're making this into a better electrophile by transferring it over to something that we can actually attack. So this would be something like our protonation sort of step. And then we've got, let's say, our water. Water is going to tack in to make our tetrahedral intermediate. So we're still following the normal balance that we've discussed as we go through our activation of our carbonyl, followed by some sort of a nucleophilic addition to give us, remember, under acidic conditions, we're going to have protonated intermediates that we're carrying forward. Now, okay, why did you protonate on the oxygen? Remember, this is under resonance. That cation that you have there is under resonance control, so we're not really localizing it specifically here, just for the point of geography, of showing you where that pi bond is to match over what we've seen. Remember, this is really the same kind of component. So what we've done here is we've activated the carbonyl, we've done a nucleophilic addition, we brought in our center, and what we're going to do is a series of proton transfers. Just like we've said before, if this is not a very good leaving group, if this was something at Fischer esterification, what we need to do is first get rid of the proton on the water center. We brought in this nucleophile. We want it to stay there, so we don't want that extra O+ to be remaining. And we're trying to get rid of that nitrogen. We want to actually lose this component as our leaving group. So we have an extra proton here, and we're missing a proton there in order to allow this mechanism to go forward. Now again, this is one of those cases where energetically, we want to come back to the amide as much as we possibly can. The only reason it's going to move forward is if I have enough water present, Le Chatelier will just help drive this equilibrium forward over time. But the energetics of this one are already not in our favor. So after those two proton transfers, we're going to end up with our OH, OH, and NH3+. So we've locked in the sigma bond on our nucleophile. We've now protonated on the nitrogen to make it ready to be a leaving group. So this is similar to what we've seen for something like the Fischer esterification. So now we're going to bring the system together where we're going to collapse this group, bringing in this component and kicking that part out gives us back our pi bond. And we've now ejected NH3. Ammonia is now the group that we're at least kicking out from this component. Now that we've generated this, you've got a pretty good base as well as a very strong acid. There can be an acid-base step that allows us to deprotonate to give us our final compound. So this is where we have our OH, NH4+. That proton there in our final component, remember any other base that might be here, or at least to regenerate the acid in the system, we still have water present. Water's job there is going to be picking off this last proton, and the system is going to be sitting probably as this carboxylate, our H3O+, and NH4. So in the end, starting off with our strong acid system, we're using it like we did with Fischer esterification to activate our carbonyl. That activation to our carbonyl allows the water to add into the system, and we're setting it up so that we have to both eject the ammonia as a group. Most importantly, we're trying to do that so that we don't eliminate at this step right here. If I just tried to sort of collapse this group out and knock this out without that protonation, I'd be ejecting a nitrogen minus. That's a really, really, really high energy system. It's better to protonate it and then allow it to distribute out. But yeah, once again, this is on an energy surface where most of these things are not super favorable. If this was something that we were doing by Fischer esterification, similar kind of reaction and overall control, just normally what we'd end up doing there is driving the reaction forward using Le Chatelier. So that's our final sort of point. This is just drawn out in ChemDraw, where what we're doing in this specific representation is we're just coupling together the acid-base step at this point right here, rather than showing what I drew through. They're equivalent, right? We're just showing which step the two proton transfers actually are passing through. Again, having this sink here, releasing this ammonia, is something that allows the chemistry to sort of move forward, because by ejecting that nitrogen, we're giving a proton sink a better base for the system in order to suck up that proton and help this reaction move in. It just also means that as this reaction runs, you're going to be slowly losing proton efficiency. If we start off with only HCl in the system over here, a very strong acid, as that ammonia is being generated, you are kind of knocking down the overall efficiency by creating the strongly basic system as it goes. It just means you're going to have a lot more acid to make this happen. But functionally, this is what's going on in that second step of your nitrile hydrolysis. We talked about the Strecker reaction. This is that back part of the Strecker reaction for the hydrolysis that you guys have seen before. So the basic mechanism is the weird one, right? This is the point where we will stop at that amide intermediate. It's much more stable under these conditions. So the Strecker chemistry usually will go to the acidic hydrolysis just because that protonation allows that nitrogen to be your better leaving group. Under basic conditions, we don't have that case, but you can still force it forward. Yes?
I have a question about the previous slide.
Yep.
If we do this in the lab, would we use catalytic amount of acid or sludge different?
you're going to use stoichiometric. You have to, right? If you only use a catalytic amount, let's say we add a tiny bit of this acid, what that's going to do is activate this kicks out, add up over here. Because that molecule, that's your catalytic acid, it's going to get trapped over there. You're dramatically diminishing the ability of that proton because it's now stuck as an ammonia rather than, let's say, HCl. So this is going to require you to have a higher concentration of the acid to make it work. Can work catalytically, but your efficiency is going to drop off very quickly, right? It's still technically acidic under these conditions. It's the ammonia salt of it. It's just that it's not nearly as strong. So base presents the interesting problem because now you no longer have this activation. The good news here, if you look at your overall reaction sequence, remember the 3 general mechanisms we talked about for acyl substitution? We've got good electrophile, good nucleophile. That is not either of these cases. You've got strong acid. That's what we just showed you last time. This is something where we've got a pretty good nucleophile, pretty bad electrophile, right? The good nucleophile we have here is things like our hydroxide. It's this O- that we're using in the system to actually push this reaction forward. Now typically, again, we're going to use strong base under water and heat. And the key is this. The other part that we'll usually add to this one too is time. What we'll do is we'll say that over 24 hours we're heating, something that gives us some part where we're saying we're giving this a long time in order to drive this to completion just because it takes a long time. You're using something that's energetically relatively stable and you're climbing uphill. The overall mechanism looks as follows. What we're doing is nucleophilic addition to my carbonyl. So this is following that first addition step that we've drawn through already. Nucleophilic addition to that carbonyl is only possible because you've got a strong nucleophile, this O-, that's adding to that carbon-oxygen system. Once we've done that, we now have this oxyanion, so they're about the same energetics. The overall stability of this oxyanion versus this oxyanion is about the same. From there, though, what we have to do is, once again, get this system ready for protonation. It means pulling off a proton and coming up to this zwitterionic intermediate. Relative concentration, this is going to be very low. It's not a very feasible reaction to add a proton back to your nitrogen under these basic conditions. But effectively, you have to get another proton onto your nitrogen to allow this to happen. Without this step, what you'd be doing is some kind of an ejection where you would be making NH2-, and that's forbidden, right? This is something that we'd have to be pushing off something like LDA in an aqueous solution. If you actually go into these details, the way this is actually following up in a reaction that we would call sort of a coupled reaction. So everybody, again, ideally, you guys have had breakfast that had some protein in it at some point. This is the step that we actually are doing in our cells, right? Hydrolysis of amides to break down peptides is using this kind of a system where you're starting off with, in this case, instead of an amide, you have an amino acid. This is your protein backbone. And what you're doing is your enzymatic system is bringing in water as your nucleophile. That's your catalytic triad, is using this oxygen from your enzymatic system like water. It's installing it, helping to sort of hold it in and actually attack into your carbonyl. And then it's helping with the proton transfer to make that nitrogen leaving group more feasible. Usually it comes from an amino acid like imidazole. Yeah? Well, the second it comes out, yes, it's a gas, but it's surrounded by aqueous, right? Like you are in an aqueous environment, and it's only coming out one atom or one molecule at a time. So you're not making so much ammonia that it just bubbles out as gas. As soon as it's generated in the system, you have all these protons available from water. We're pulling a proton back from that water to turn it to ammonia plus, like this, an acid-base reaction, where this would make it into NH4 plus. Is going to be preferable. So it remains solvated because you're typically in a highly protic environment. You're right. If you ran this in something like, if there was no protons available anywhere else, then yes, you would be making ammonia gas from it. But that's also where the only way that this whole reaction can work is you have to have this bath of other protons available to help with this proton exchange, right? It doesn't really work unless you have a protic system as well, too. So what we're going to do next is, this is where another part we're going to start to practice as we move into this part of the course, is not just starting material and conditions or starting material and product. This is kind of the hardest version of these type of reactions that you guys have to transfer through. Given conditions and product, where did you start from, right? This is kind of thinking backwards from these type of cases. So we'll walk through this, and also I'm going to focus on a strategy for how to do these kinds of questions. Again, I'm mentioning it right now that as you guys are practicing, you've been working through starting material and conditions equals question mark. You've been working through starting material and product. How did I get there? If you've practiced those ones, taking those same type of questions and omitting your starting material or generating ones where you have conditions in product gives you one more level of practice and control to help revise and basically focus more on the chemistries that we've been talking on. So that's the last that we've got for changes out of our components. The last reaction that's very useful, though, is if we can turn nitriles by hydrolysis into amides, and then amides back to carboxylic acids, we've got the reciprocal we can do as well, too. If I had a primary amide from some reaction, I can use a reaction like this to convert it back into a nitrile. So this is the reverse reaction that we did starting at the very beginning. Instead of just hydrolysis of nitriles, we can actually take amides back into nitriles. And the way that we're going to do that is using our secret reagent. This is our thionyl chloride. Now remember, as a name, we talk about thionyl chloride as a dehydrating reagent. Its job is to activate systems like this. It's a very, very powerful electrophile. As the reaction is running, it's doing two things. Now remember, where did we see this before? What was thionyl chloride good for? What did we use it for? What's that? You make acid chlorides from it, right? You guys remember this, or you're introduced to this by taking carboxylic acids plus SOCl2, and the job there, actually I'm going to recolor code this. This is kind of the makeup of what we had. By putting these together, we are making our carbonyl. We're installing the chloride. Its job there is to act as a nucleophile. The sulfur is doing two things. It's leaving as SO2 gas. That's partly what's driving this reaction forward. But more importantly, it's also capturing that oxygen. So this is why we call it a dehydrating reagent, is because it's giving a chemical sink to the oxygen that we started off with, but it's also, that's being lost here as gas, but also the hydrogens that you're generating from this one, where we started off, this hydrogen over here would eventually be lost as something like HCl. This is where we could have a potential sacrificial base in that system as well too. But effectively, water in this case is being converted to something that's not water anymore, and we can get it out of the system. We're effectively doing the same thing here. It's still a dehydrating reaction. Doesn't look quite the same because if you look at it, there's no water in this case. But remember, if I draw this system like this, what if I was to redraw this as a tautomer? So the tautomer I could draw my amide as is R double bond NH OH. And I'm only doing this again. Remember, this is not the most stable tautomer, but I'm just drawing this from a point of analogy. Now in this tautomer one, this kind of imine type system, it looks a lot more like our carboxylic acid. Now you can kind of see where the water is in this case. You've got this H2O that we have to remove. That's how we get to our nitrile. So it's still a dehydrating reaction where we're pulling oxygen out of the system and protons effectively. It's just that where they're distributed here looks different than what you've seen before in the carboxylic acid. So given that that follows a similar logic, the mechanism is going to be really similar too. We're going to start off with our amide and our thionyl chloride. And again, usually we're just going to run this potentially without a base. It's possible to have a base added to the system. That felt very Trump. I don't know why. Start me off. You guys have seen this before. If you start from a molecule like this, if this was a carboxylic acid and thionyl chloride, what's the opening move? This is where a week of break has a lot of cobwebs, and now you have to sort of throw them off. What do I do? Well, what's my nucleophile in this system? Yeah, amide is your nucleophile, thionyl chloride is your electrophile. This is going to look something like that activation, like this. So what you're doing is you're starting off by making that carbonyl way more activated. This is the same opening we did for our acid chlorides. And again, you can draw this in a couple different ways. Either I'm going to draw it as, let's say, just the pi bond, or sorry, the lone pair is the thing that attacked. That's going to get me this SOCl, Cl minus, and NH. I will have a positive charge over here as I've drawn it. The other option, if you'd like, you could draw this as lone pair like that. This is basically just the resonance equivalent of it. We're leading from the lone pair on the nitrogen out to the oxygen. And again, the reason I'm doing this is because in the end, I want to form a sulfur to oxygen bond, so I'm focusing on that as a case. From the blue arrows, just want to draw that one out, that might look like, sorry, let me draw it over here. O, sulfur, O minus, chlorine, chlorine, and we've now made a double bond onto the nitrogen, hydrogen plus, like this. Remember, these two are just resonance isomers of each other. We're just sort of showing where localization of that charge happens to be, and we're just showing formally which electrons are involved in it. But fundamentally, what we're doing here is we're sliding over we're making an oxygen to sulfur bond in order to help get that into a better electrophile. We're getting that oxygen sulfur bond because this is what I actually want to eject from the system. And in the end, I'm going to go, let's say, from this guy here, dropping this down and kicking out the chlorine is going to give me my OS, double bonded O, chlorine, NH, H, positive charge still sitting here. Where, again, the resonance isomer of this guy would be where we have a single pi bond onto our sulfur, double bond over here. From that green structure, it's a little bit more useful because if you imagine what we're trying to do here, the number of bonds we have to make, if we're pushing ourselves towards a nitrile, we want, in the end, a carbon-nitrogen triple bond. We're trying to form an oxygen to sulfur bond because we're losing that piece. So once we've shown that green structure in the bottom corner, you can see you've just done two very important steps. I have a new oxygen to sulfur bond formed here. I now have one carbon to nitrogen pi bond in place. I'm moving towards my sort of overall target. Okay, once we're here though, I need to get rid of this charge and I want to keep moving this reaction forward. I'm going to generically say that some base, remember as I do this ejection, I'm also going to have chloride kicking around here, so that could be your base of interest, or more generically, any base in the system. It could be your solvent, it could be pyridine, something like that. A base is going to pick off this proton and get us back to something that is now neutral. O, sulfur, double bond O, chlorine, double bond nitrogen, H. And we're going to have our, I'm going to call it base plus H. Okay, first one's done. Now we're kind of basically doing an elimination reaction, right? What I need to do to kind of move this forward is I need to make another carbon-nitrogen pi bond. I still have a hydrogen that's kicking around there. Nice thing too, though, is I've got that really awesome leaving group. This piece right here is kind of like that anhydride. If I could clip this bond right here, I'm losing my SO2. I can use that to kick out my Cl-. All I have to do is tug on that proton. And again, this is unique for the nitrogen because in the case of doing an acid chloride, that's an oxygen over there. There is no other proton there under the neutral species. The nitrogen, because we've got these two protons, higher valency, we've got some way to remove that last proton. So let's say we take another molecule of a base. I'm going to deprotonate here. As I do that, it becomes what looks like an elimination reaction. So if I just drew it, for now I'm just going to draw it, oops, like this. We're going to deprotonate, create this, and I'm just going to eject this. We're going to kick this off as an O- as our leaving group. Think of that like an acetate, right? If I was adding to an anhydride, we can potentially break that piece off here. So that's going to give us our R carbon triple bond nitrogen. That's our nitrile species. The other part is O sulfur double bond chlorine minus. That's the anion that you're ejecting from here. But remember, this had a special fate. A molecule like this is rigged to self-destruct. This is that molecule that little fragment is one step away from doing another elimination to give me SO2, which is my gas, and Cl-. So that decomposition is what helps to final this whole point off. Overall, one of the oxygens ending up with the sulfur, the 2 protons that used to be on the nitrogen, both of them end up with a base, could be Cl-, could be an exogenous base that you're adding to the system. That's the overall sequence, which is very, again, you should recognize this as a very similar overall transformation to what you've seen from acid chloride formation. Yeah?
On the last step, why don't we add in the nitrogen lone pair to pick up the sulfur compound instead of deprotonating?
So you're saying take this here and do which? Like go that?
No, take the lone pair on the nitrogen to
That-
the triple bond
Oh.
instead of deprotonating.
Oh, same, 6 and 1/2 a dozen the other. Like, so what you're saying is, why, instead of doing this deprotonation step, why don't we just do that and that, right? And then again, if you drew that out, what that would give you is carbon, triple, nitrogen, positive, which is now super acidic, and we lose the proton. So what we're saying here is the functional equivalent is I need to remove that proton, either kicked off by base or as a result of the two, right? Either way, similar, you're getting to the same place. Honestly, I think that both of them have equivalent. You might try to break it down again. That's nuance. Maybe with a very strong base, you're preferred to the first versus the second. Remember, the problem with this whole sequence, though, is the nature of your base. That's one part I do want to comment on. This here has to just be a base, right? We do not want to be using something like hydroxide, right? If I ran this chemistry where I used sodium hydroxide added to the system, what would happen if that was what I was setting up? Yeah, if you went in with a molecule that's both a base and a good nucleophile, this is where you're going to have a very bad day. It's going to end up being a very exothermic reaction because it's going to attack only that system. We were setting this up where we're using a relatively light nucleophile with this. So the only base that would sort of work with this system might be pyridine, triethylamine, one of our non-nucleophilic bases we've used in other sort of systems, right? Okay. So now, this is your whole landscape. And we tried to break it down. We've actually got a map here of which lecture we talked about which pieces. So we started off, lecture 16, our interconversions of our carboxylic acids system. 17, this is where we're taking our acid chlorides down to our other components. 18, this is our anhydrides down to these other ones. And now 19, this is our retro back in. So this is your full summary for all the different species and all different transformations that we talked about the last couple days. But again, the thing that's really important about this is the common principles, right? Each of these reactions is involving some kind of a carbonyl Tai Chi kind of step, right? You're actually moving electrons up into the carbonyl, dropping them back down again. And what makes this possible is you're actually using a nucleophile-electrophile pair. The one that we're going to just briefly bring over is a molecule, a functional group called an isocyanate. So isocyanates are this guy right here. What is, just as a quick part, what's the hybridization of that carbon? sp3, sp2, or sp? sp, right? That's because it has 2 pi bonds. They're just stretched out to either side. That means that in the final, if anybody does this, why? What's the geometry? Yeah. There would have to be linear, yeah. The carbon in the middle here, sp centers in that one have to be a linear geometry. So you're drawing this, when you draw this functional group, this is nitrogen, which is linear to carbon, which is linear to oxygen. One other part too, you may see this in certain parts, but that's why annotating it like this, where you actually got the molecular equivalence, is very useful. One other way you may see the isocyanate drawn might be nitrogen, double bond, oxygen. When it's drawn like this, there's implicitly a carbon in between the two, right? We are not trying to say nitrogen, whoop, whoop. There is a carbon right there, and usually that's indicated by a break in the 2 lines like this, right? So that's in case you've ever seen it. If it's not designated as an actual carbon, there's a dot or a break in those 2 lines, which is implicit to that, right? You know that's what we're trying to communicate. Now, the thing about isocyanates, they're basically carbonyls. They're the same thing as anything else. They have the similar reactivity of things like anhydrides. Where they actually stack up is they're activated systems that you can use for all kinds of other transformations, which gives us this secondary tier of reactions. So whereas before, if I took, let's say, an acid chloride and I added a nitrogen to it, I would make an amide. If I took an acid chloride and I added an oxygen to it, I could make my ester. Acid chloride plus water would give me my carboxylic acid. So what I'm doing there as an analogy is to say that this isocyanate, really think of it as similar to something like carbon, double bond, oxygen, chlorine, R. That's the fully carbon equivalent. Now that we've got this guy next door to it, you're just bringing along this extra nitrogen on the other side of the carbonyl. So here, my nucleophile would be nitrogen, where the isocyanate part is nitrogen, carbon, oxygen. If my nucleophile was an OR, alcohol, we get these carbamates or urethanes, where the nitrogen, carbon, oxygen was the isocyanate. And then finally, if my nucleophile was water, then my isocyanate is from my nitrogen, carbon, oxygen. These are really useful because not only super electrophilic, they follow the same patterns that you've seen with things like acid chloride type additions. The difference is, because we've got this nitrogen adjacent to them, they end up as these linear structures to begin with. But the additions are very similar. You're still adding to the carbonyl in the same sort of way. So that's where water is my, color coding it. Water is my nucleophile, alcohol is my nucleophile, and amine is my nucleophile. It gives these other points. And you've heard these words before too. You've probably heard of things like polycarbonates or things like urea compounds, carbamic acids and stuff. These are molecules that you've probably seen both in materials and other things like textiles. So last one is the organometallics. If we take an organometallic reagent like Grignard's, alkylithiums, if I tried to do this reaction, and you guys have seen this one a couple times, what's your product from this one? Acid base, exactly. This is where these guys formally are carbon minus equivalents, right? They're really, really, really strong bases. So under these conditions, that is my acidic proton. I'm just going to get acid base. If I just take a carboxylic acid on its own, I am making just this. Fun fact, let's say I take butyl lithium, right, as my lithium species. If I took a carboxylic acid plus butyl lithium, you are making what? What's the carbon chunk of this? Butane. Butane is a gas that everybody has in your lighter. That's why you don't do this, right? This is fire. This is where you're making a flammable carbon system plus heat, which equals flames. So you cannot do a direct reaction on these carboxylic acid systems. Carboxylic acids are completely not allowed in this point, which means if we're going to do additions, that Y group we have for these other acyl substitutions must be something that is aprotic. This is where we have esters. This is where we're going to have anhydrides or something else. Yeah? Okay, then that's still flames. Okay, but good question. Number one. If I just hit it harder, what is it? When brute force doesn't work, you're not using enough brute force? Is that the thought? But no, let's stop on that. So number one, if I add a first equivalent here, yes, I make this and I make that. And let's say I survive that addition. Now, if I add more, is this nucleophile here able to attack an anionic carboxylate? Shields up. This thing is not electrophilic in any way, so there's no way a carbon anion is ever going to approach that thing. They're going to hold out to each other, and there's no addition that's possible. So, no. This is where, if we're going to do this addition, what we have to do is come up with something that's typically aprotic. And it means that we're going to do some type of addition where this Y is equal to something like our alcohol. So this is our esters or our amides, right? Those are all possible that are potential ways to sort of add into this one too. Specifically, if these are our esters, one of the important things that we see here is that starting off from this higher oxidation state, something where this is like an ester and an anhydride, the product you get is not one addition, but actually two. When we do this, starting off with an organometallic compound, we're adding two equivalents to this system because what we're doing here is the carboxylic acid derivative. If you remember your oxidation state, this is something where you've got a carbonyl, carbon oxygen, if I go through this addition, what's the intermediate product that I form? So let's say, for example, if that Y group, if this was our ester, and if I do an addition where I'm taking a carbon minus system into this, remember, that's where we go, nucleophile goes in, comes back up, pops back down, kicks this group back out. That will give you a ketone. What's the relative reactivity or electrophilicity? Ester versus ketone. Who wins? Who is more electrophilic, a ketone or an ester? So you just took a reaction and you made an electrophilic species which is more reactive than the thing you started off with. It means that under most conditions, you will not stop here. You're going to take a second equivalent of your R minus, and you're going to do the same point. That's why you end up with these two additions. Simple organometallic addition to your carbonyls is a really simple way to add to it, but since carbon is my nucleophile, and because I'm kicking off this OR group, you're making a more reactive intermediate, which is going to jump through. This sounds like what? We did this before. Started with bromine. Remember this? If I take base and bromine and I try to monobrominate, I make something that's even more reactive, so the dibromination and the tribromination happens. This is in that same camp of reactions where the intermediate you generate can still react and is actually more reactive than you started off with. So how these additions are going to work is my Grignard nucleophile is going to attack. That's going to give me my OR minus. Your Y, whatever this is your leaving group, and you've got your R prime nucleophile. That's the same tetrahedral intermediate we've been going through. The difference here is that when this group pops back down, that's where we're generating our ketone. The ketone is in the presence of more Grignard, and that will undergo a second addition. Once we've done that, though, now we're kind of stuck, right? O minus is sitting here. We've got our first R prime, like this. We've got our second R prime, like this. Now, that tetrahedral intermediate's got nowhere to go. We've parked this O negative charge. If we were going to try and bring it back down again to reform my carbonyl, well, the first blue R, that's a carbon chain. We're not kicking that out. Purple, that's a carbon chain. Red, that's a carbon chain. Now you're stuck. You've made this compound, which is a tertiary alcohol, right? It's a primary to being a tertiary alcohol. On workup, where we add our protons, that's where this is going to turn us into our OH, and we have both other components, R and R prime. So there's two things that you cannot do. You cannot take a carboxylic acid, and hit it with a Grignard. Nothing happens. You can convert the carboxylic acid to an ester, but if you try to hit the ester, you're not going to do it a single time, you're doing it twice. If you want the carbonyl, if you want to stop at this intermediate, this is where we need special circumstances, special conditions. So this is the description that we've gone through. The reaction is not going to stop at the ketone. It cannot be isolated because in the process of the reaction, as we're running it through, it's going to form, it's going to be reactive, and in fact, it's more reactive than our starting material. So moving that part through to our product is going to be what happens. In fact, if you tried to do this using only one equivalent of Grignard, you tried, well, I'm going to titrate my way around this. You're going to end up with still none of this. You're going to end up with some of this and some of this as a mixture. It's almost impossible to do this by a titrometric way. You really have two choices. Do it twice or don't do it at all. So it's not something that you can do just by titration. And again, it's only because of the relative reactivity of that ketone. So what do you think happens in these cases? If I took excess methyl magnesium bromide or excess phenyl magnesium bromide to these two cases, what are your products? Okay, let's start with the second one first. I'm going to take excess phenylmagnesium bromide. I'm going to abbreviate that as pH, right? pH MgBr. If I add this is my standard addition where that is my carbon minus. It's my delta minus system. I've got my delta plus over here. I will add 2 equivalents of this, because under that addition, that's going to be my leaving group. So I'm going to expect this is going to be my first phenyl group, the one that came in on my carbonyl and my carbon. That's the carbon center representing my carbonyl. And I'm adding 2 equivalents of my phenyl, after workup, OH. Where I'm also got your other carbon stuff, your alcohol will be ejected simply as methanol in this case. What about the top one? It's a similar kind of concept. You got a carbonyl. You're adding to the carbonyl. You have 2 different carbonyls. We have red, blue. Which one wins? Remember this back. This is the last thing we did just before the break. This is what we call a what? If I had to give that thing a name, that's not just an anhydride. That's a mixed anhydride. Red or blue? Which carbonyl is my more susceptible carbonyl? Blue. Why? Sterics? Electronics. This carbonyl, red has stabilization here and here. Blue has only this one. Electronics is going to favor the blue one. So you're going to add to that carbonyl. So decomposing it, that means I'm going to add to this carbonyl. That's the bond I'm going to break. All of this is my leaving group at that part. So now if I'm adding to that center, this is my carbon fragment. So let me draw that part. It's going to look something like this. You're still going to do 2 additions. In this case, my Grignard is my methyl. So I'm going to have 1, 2 methyls added to that center. That should be the product that I generate. So this has both chemoselectivity, which carbonyl am I going to hit, and also fragment-based ones. What's my electrophile left over? What's the nucleophile I'm adding to? Doesn't change the fact that you're going to hit it twice. It's the same overall mechanism where we're still going to eliminate, make an intermediate carbonyl, and then add again. So last thing is this super, super important fact. If you want to stop at the ketone, you start with the nitrile. So this is one important case where if you really, really want to get just the ketone out, you don't start from the ester, but at the same oxidation state is the nitrile. This is still carbon triple bonded to 3 of those. This is a case where 1 equivalent of my Grignard will give me my nitrile. So that what we're setting up for here is we're starting to show you patterns of reactivity where you have 2 different kinds of classes of reactions. Like the other Grignards, these ones here, these are kinds of reactions that are forming a more reactive electrophile as the reaction is running. You have no choice, the electrophile is being exposed. We're going to go over the mechanism of this one next time, but this is a case where the more electrophilic species is hidden until the workup. So, all right guys, I'll see you on Wednesday. Okay, so for our problems, for this one, we're asked, as I mentioned in class, to identify the starting material. And this is a little bit of a different action than maybe we've been used to. But as I mentioned before, it's a good practice to look back at some of the old problems and play this game of either trying to identify the starting material given the reaction conditions and the product, where also we can have the starting material and product where we're trying to identify reaction conditions, or then finally the more traditional starting material conditions, and then we're asked to identify the product. Remember, any of the reactions that you've been given right now can be used to practice by trying to omit one of those pieces and coming up with either a flashcard or problems to test amongst your study groups. So in this case, we're using acidic conditions and heat. This is our amide hydrolysis conditions, as we mentioned over here. Since we're trying to do amide hydrolysis, what we're looking for in the product is the 2 fragments that might have been an amide to start off with. Remember, when we have an amide, what we're looking for is the carbonyl was attached originally to the nitrogen. So this was probably something where we've added
one molecule of water, meaning that this was a ring where this would be nitrogen number 1, 2, 3, 4, and carbonyl number 5. That's what was making up the amide structure. So I'm going to draw this out as a 5-membered ring like this. And then on this would be nitrogen number 1, carbon number 2. There's 2 methyl groups. 3 and 4 are CH2s, and 5 is our carbonyl. Now note this out too. Remember this molecule, if you remember the name, this is a cyclic amide. We have a special name for that. That is our lactam. Okay, for this question, we're asked to draw both the mechanism and the product from this particular transformation. So we're adding a Grignard to our acid chloride. So in this case, the acid chloride is our electrophile. The Grignard component to the center here, that is our carbanion. This is our nucleophile. And since we've got an excess of this one, this is our first addition, where the second step here would be our workup. So how we can draw the mechanism for this, we're going to start with this as our nucleophile, and we're going to do our addition to the carbonyl fragment. That's going to give us our oxyanion, and we're going to have our alkyl fragment that we've added in, and our leaving group is that chloride. So this is our strong base type conditions. We're going to then eject that chloride to give us this fragment here, like that, to give you this component. Now that's the ketone intermediate. Remember, since you have excess of this Grignard, we're going to do a second addition where we have more of this magnesium bromide structure, which means we're going to do another addition to that center to give us a new oxyanion, and now we have 2 equivalents of this Grignard added to the fragment, something like that. Now it's only at this step where we add, let's say, our water to this one. This is where we're going to get the addition. So let me draw that out so you can see the bonding. So water like that. We are going to then pick up this proton to make our base, and that gives us our final product. So we're going to have this as the tertiary alcohol, 2 equivalents of our Grignard added like this, where that proton right here came from the addition of our water. So this is that second condition where we're taking a Grignard addition, we're using 1 equivalent, and because we're now adding to this nitrile, this is the type of reaction that allows us to actually control the addition to make only a single component. So let me draw this part out. The mechanism we're going to be talking about here is our methyl C triple N. And we're adding this ethyl magnesium bromide, that's our nucleophile. So what will happen is we're getting a carbon addition, and then just like the other kind of ones, that first addition is going to punch up onto this nitrogen. So again, this is possible because we've got a very strong carbon minus kind of nucleophile. That's why we're getting this sort of generation of this nitrogen anion. So when we go through this, we will get now a double bond to this nitrogen. We've added our ethyl group to this one, and right now we've got this negative balanced off by magnesium bromide positive. So this is an ionic complex that's sitting here. So this is actually based on this mechanism. This is why the reaction can stop. Note now that what we have right here is like an imine, but it's right now negatively charged at the center. So that negative charge means right here we do not really have any substantial electrophilic character. Having that negative charge there is very similar to the kind of protection that we get when this is a carboxylate. So there's no possibility of having a second equivalent of our ethyl magnesium bromide to attack in this point. That nucleophilic attack, this is not very electrophilic because of, again, the negative charge you're seeing over here. So that allows the reaction to stop, to freeze out at this particular intermediate, and it'll wait until step 2, where we add our H3O+. It's only then, when we add this water, that we're going to get protonation to give us now our primary imine. So in this second step, we've actually no longer have any Grignard. We've added our acid proton. We've protonated this imine. Remember, this is in the presence of now water, which means we can now take water, this imine, and we have acid catalyst. That allows us to hydrolyze this imine. It's the same conditions we would do for hydrolysis of our imine to give us our final product, which would be, let me just keep the color coding, this ketone, and the fate of that imine is just our ammonia, or actually, because it's under acidic conditions, it'd be the ammonium salt of this one. So the nitrogen would be released as we get back to our ketone product.